Good morning, my dear students. I will ensure that my pace of speaking is slow enough so that you not only listen but also observe, analyze, and comprehend the concept. Let me make it very much clear that we will not just solve a single question or derivation but will also develop an understanding of the related and interlinked concepts so that by properly solving a single question you are able to solve numerous other similar and related questions with ease and confidence. Today we will learn to derive electric field at a point on the axis of a uniformly charged ring. The axis is passing through the center of the ring and is perpendicular to the plane of the ring. Now we will draw the diagram required for this derivation. You all have to draw this diagram here and now. So pause the video so that you are able to understand the question further. Here in the diagram, lambda is linear charge density on the ring and its value is equal to Q by 2 pi r. Q is total charge on the ring and you have to put its value with proper sign. R is the radius of the ring, C is the center of the ring, A is the point on the axis of the ring where we have to find the electric field. X is the separation between C and A. dl is an element having dq charge. dl is basically the elemental length. dq is the elemental charge. dE is the elemental electric field at A due to the elemental charge dq. We will solve this derivation with the help of integration. So I will request the biology students not to be afraid of integration. Be careful and not fearful of integration. As you all know, in physics we come across numerous physical quantities. In integration, we assume that a physical quantity can be divided into infinite number of infinitesimally small components, and each such infinitesimally small component is called an element. The magnitude of an element is so small that its value is very close to zero but not zero, which in the language of mathematics is called as the value tends to zero. As we can clearly observe from the diagram that the complete length of the ring is 2 pi r and the ring can be divided into its infinite number of elements, and the length of each such element may be taken as dl, which is the elemental length and is infinitesimally small. dq is the elemental charge on the elemental length dl, and dq is equal to lambda dl as shown in the diagram. dE is the elemental electric field at point A due to dq charge of an element as shown in the diagram. Electric field is a vector, which means that it has both magnitude and direction. As you go along reading physics, you will observe that the knowledge of vectors is very vital for NEET and IIT JEE. To solve a question, we have to often resolve a vector into its components. Usually a vector is resolved into two rectangular components. one component is along the x-axis and the other component is along the y-axis, and both these components are mutually perpendicular to each other. As shown in the diagram, elemental electric field dE vector has been resolved into dE cos theta, which is x component, and dE sin theta, which is y component. So far we have talked about elemental electric field dE at the point A due to a single element dl. Now if we consider all the elements of the ring and resolve all the elemental electric fields into their rectangular components, then we can see from the diagram that y components of all the elemental electric fields, that is dE sin theta, will cancel out each other, and x components of all the elemental electric fields, that is dE cos theta, will add up. Some of you might be thinking that why dE sin theta components will cancel out. If you see the diagram carefully, you will observe that if we consider any two diametrically opposite elements on the ring, then dE sin theta due to these two diametrically opposite elements will be in opposite direction and hence will cancel out each other in pair. Now to add up all dE cos theta components, we will apply formula of integration. Because we cannot add infinite number of elemental electric fields by simple addition method. We have already conceptually solved the question. Now we have to only put the values in the mathematical formula of integration and you will get the answer. As all of us know, the formula of electric field due to a point charge q is kq by r square, where r is the separation between the point charge q and the point where we have to find the electric field. Now we will apply this formula here. As shown in the figure, we can consider each elemental charge dq of the elemental length dl as a point charge. As per the Pythagoras theorem, the separation between any point charge dq on the ring and the point A is square root of r square plus x square. We have already found the value of the elemental charge dq, which is equal to lambda dl, and the value of lambda is equal to q by 2 pi r. Putting all these values in the formula of electric field, we will get the value of the elemental electric field dE equal to k dq by square root of r square plus x square. Now, as per the Pythagoras theorem, cos theta is equal to base by hypotenuse, which as per the figure is equal to x by square root of r square plus x square. Now simply put the values of dE, lambda and cos theta in the formula of integration as shown in the video and solve. You will easily get the value of net electric field E net at the point A on the axis of the ring. As you can see, dl is the only variable quantity and all other quantities are constant. Since integration is applied in respect of variable quantities only, so we will keep outside all the constant quantities as shown in the video and will do integration with respect to dl. While applying integration, we will need lower limit and upper limit of length of the ring because dl is the element of the length of the ring. minimum possible length of the ring is 0 and the maximum possible length of the ring is 2 pi r. So the lower limit of integration is 0 and the upper limit of integration is 2 pi r. At the end of this video you can see how I have integrated dl from limit 0 to 2 pi r. So you will get the value of the net electric field as E net equals to kqx by r square plus x square to the power 3 by 2. And the direction of this net electric field is along the axis of the ring. Here you should be careful while keeping the value of q in the formula. You should always keep the value of q in the formula with proper sign, either positive or negative, as the sign will show the direction of the net electric field along the axis of the ring. As you can see in the figure, if lambda or q is positive, then the net electric field is along the positive x-axis on the right hand side of the ring and along the negative x-axis on the left hand side of the ring. And if lambda or q is negative, then the net electric field is along the negative x-axis on the right hand side of the ring and along the positive x-axis on the left hand side of the ring. As you can see on the right hand side, I have written the formula for integration, and on left hand side I have applied this formula for integrating dl limit from 0 to 2 pi r. You can also see that on right hand side I have written a function L to the power 0 is equal to 1 because I have used this function while integrating dl. One should always keep in mind that any quantity raised to the power 0 is equal to 1.